It's a pleasure to welcome Dr. Vineet Vashista from IIT Gandhinagar. He's an associate professor there, and he leads the Human-Centered Robotics Laboratory. So he earned his PhD in mechanical engineering from Columbia University in 2015 and a master's in mechanical design from IIT Delhi in 2008. His research focuses on human-centered robotic technologies inspired by human motor adaptation, and it has applications in rehab, wearable robotics, and performance augmentation. He's supported by major national and international funding agencies, and his work investigates neuromusculoskeletal processes to design devices that measure and influence human movement. So Dr. Vashishta is a recipient of the Haryana Yuva Vigyan Ratna Award in 2022 and a member of INYS INEAS in 2023. So Vinit, it's a pleasure to have you here. And as usual, it's a pleasure to have all of our audience joining us every week. So please take over. And to the audience, just please mute your microphones. And if you wish to ask questions, just raise your hands. And once Vinit spots it, he'll let you know if it's good to ask. All right. So all over to you. Thank you.
Thanks, Aditya. Thank you for having me here. It's a pleasure, and thanks for introducing. So, hello everybody. This is Vineet. So, I work on human robot interaction, and we have a lab at Human-Centered Robotics Lab at IIT Gandhinagar. So, the topic that I thought maybe I could spend time on today is something to talk about beyond developing wearable system, right? Something that we do develop wearable systems. So I think we will talk about that, but then how does they affect us? How do we plan for it? And I think I will like to take two studies from our group. I will give you a brief introduction and some time on that. Half of the talk will be on that, and then plan to take two studies. Depending on the time, I may cut one, or we will see. So yeah, first come first. So if you're visiting IIT Gandhinagar, do stop by. This is the time when we start looking like this, and we continue to look like this over the rest of the this year and maybe close to the next summer. So to begin, let me use this caricature. So all our movies are, I think, are putting us in this direction, right? So the way things are moving, maybe the human himself will become a humanoid, and humanoids are going to be among us anyway. We have seen a lot of companies working on it. But the kind of the way I approach this, I think this particular poster summarized this idea that how our society is bound to grow is not completely replaced by humanoids, but collaborating with humanoids. And this itself is a very interesting topic in itself, and I think that there should be some discussion on this part as well. But what I'm going to discuss today is something that I am wearing, and the collaboration between this robot that I'm wearing and the human himself, right? So this collaboration is as important, because it's not just a two system combined together and they are bound to perform better. This is not as trivial as it might appear, right? So let's discuss about these aspects, and maybe down the line, of course, I think this physical human robot interaction is another great idea that people are exploring right now. So what do we mean by wearable system, and what do I specifically mean by wearable system? These four pictures basically summarizes it all, right? So there could be a person working in an industrial setup, and she might be carrying a heavy weight. So there could be extra system that she is wearing, which either help her do this work more efficiently or make her less fatigued while doing it. And in doing so, what is being done is either it is killing the vibrations that are coming to my hand, or it is saving part of the weight of the device that is coming on my hands, or it is passing directly to the ground, or it is helping me stop some weight that is coming onto my back. Right. So in one way or the other, this becomes a collaborative system. By using it, I feel advantage. Now, maybe as a runner, I might not use it, but maybe if I'm climbing a hill, I might use it. Maybe I want to do some hiking. I'm old. I can use a hip exosuit, and then it can assist me. If that doesn't sounds like a good application, look at this fourth figure. There is an elderly person. She is having trouble, but I think these kind of devices could be of use. And by the way, these devices are becoming very common in our Western countries, and starting, I think in India, they will also present some application now and then. But one application that is pretty sure is the rehabilitation side. I think these devices are being used in various clinics, various mobility lab, not only outside, but in India as well. A lot of people are getting trained with it. Their effects and their usefulness are still under debate, questions, but their usefulness from the reduction in the manpower required, reduction in the trained manpower required is very well established. So these systems are being developed and will be useful. So what we use these systems for? Specifically, we can categorize them as restoration and augmentation. So what do I mean by restoration? So this video, if you might see on your screen, you see that there is a cerebral palsy child trying to walk, but she's incapable of taking the weight on her legs, and she needs a caretaker all the time. On the second video, let me reduce the sound. In the second video, if you see that there is a child, again, the same kind of neuromuscular disorder, but there are two people trying to help this child move around. Now, this is a very complicated task, right? For the patient, it's very being dependent on other people, and for the caretaker, the caretaker, multiple caretakers or one caretaker is required for one patient. So that basically reduce the strength or the capabilities of these physical therapists. So we need to do something about it. And if we look at the statistics in Indian perspective from the neuromusculoskeletal disorder point of view, the way aging is growing, we need some sort of intervention in this direction. Now, the other direction is augmentation. What I mean by augmentation is something where I am doing a task which is going beyond my normal capabilities. So let's say lifting a 40 kg weight and walking around. Maybe I'm a soldier, maybe I am working in an industrial setting, and so on and so forth. Sometimes we may think that over time technology will take out of all these loads, but that's is not actually happening. Our defense people, our industry still have people doing these tasks. And you will be surprised to know that in various European countries, I think use of some exosuit for this material handling task has been made compulsory, because they're not able to avoid material handling from the human perspective. And this material handling affect the individual efficiency as well as the healthcare. So there is a need to create these devices to help them. So that's where it is called augmentation. So now we can see that from both augmentation and restoration point of view, there is a need to develop these devices. But when we develop these devices, what do we see? We see certainly a human, that there is a human who is doing these movements. I need to understand these aspects. I also see that there is a robotic devices, right? Some of these could be a passive, but it still brings on its own passive physics to it. I need to understand that physics. I need to understand that how, in presence of that physics, human gonna behave, or vice versa. In presence of the human, how the device should behave. So we need to ensure that this interaction should be studied from the transparent, realistic, and safety manner. And this, whenever this interaction is happening, there should be an advantage of this interaction. Otherwise, there is no point of putting a robot on human. So the way to approach it is we need to definitely understand the human neuromechanics, right? So the way a human walk is a hierarchical setting. So and if you see me that my arms are moving while speaking, this is a voluntary task. My brain is sending some electropotential down to spinal cord, telling the recruiting appropriate muscles to move my arms here and there, just to convey my message effectively. But the way it happens is it's a stochastic scenario, that the electropotential builds to a certain value. Only then the muscles will be start contracting, and we will notice that each limb, either arm or leg, is having a more number of degrees of freedom or more number of muscles than we need to be recruited. So this gives us a choice. This gives us an option of optimization. What muscles to use, when to use, how to use. So for example, if I throw a ball, you can catch it very fast. You can move your arm in a different trajectory, but you can still catch it. So this redundancy is still there. The same way, when you're walking, you can walk in multiple ways. So then you generate these forces, and eventually what you see is the motion that is generated. Now, when we walk, it's not literally just like generation of the torque. For example, when I'm walking, I need to make sure that I can lift my body weight. I can walk. When I'm walking, I need to generate joint torques on my hip, knee, and ankle. But if, let's suppose, the floor is wet. So if it was not wet, I was walking and not planning my torques consciously. But the moment I see that the floor is wet, I would be doing something extra to that. What I will be doing, I will be stiffening my joints. The reason I stiffen my joint is so that I don't fall. I increase my impedance, joint impedance. So what we notice is that the redundancy in my muscle, the redundancy I have in my actuation space. What is my actuation space? My muscles in my body. I have redundancy, so I can control multiple things at a given instant of time. So when I look at musculoskeletal system, I see that it generates joint torques, but it also have the independent capability of generating this joint impedance. And that's how our CNS perform this any task. You take any example, any day-to-day task. If you are lifting a lightweight, light payload or versus a heavy payload, you will notice that you're manipulating your impedance, and you can generate these joint torques independent to each other. So what we see that there is a set of voluntary tasks that happens. So as I mentioned earlier, in the hierarchical setting, signals comes from the brain, go to spinal cord, muscles are recruited, and if the potential is enough, the muscles contract and generate the required amount of force. This is a voluntary task, but there is an involuntary task that happens. Sometimes it is called as a reflex. So there is some perturbation, some feedback coming, and some of the neurons only in the spinal cord, they have no connection from the brain, or no signal came consciously from the brain, and I create an reaction. So I'm walking on a beach, there is a broken glass over there, I step on it, and suddenly my body take a posture which prevents me from falling, and there is no involvement of brain. So these kind of things are called reflex. Why I'm mentioning all this right now, why we are having these neuromechanics classes right now? Because whenever you're going to put any external object onto the human, right? So the human will adapt to the presence of that external dynamics, and I will show you in one of the study that I will show. Then the person can take a voluntary reaction or an involuntary reaction, or sorry, voluntary response or involuntary reaction. Now, which of them, which response is kicked on, will depend upon the usefulness of the device that we have provided. Then I mentioned about the redundancy in the muscle. So this is also very critical that one needs to understand. So this cartoon basically explained to us how this happens. So when I look at my ankle joint, let's suppose only in a plane, when the leg is moving, the foot undergoes rotation about the ankle joint. Now the way it undergoes is based on multiple muscles. So if we take only two of those muscles, so this is, let's say, tibialis anterior, this is soleus muscle, they both have capability to contract. Now when one of them contract, the other needs to relax. Otherwise, the person who the muscle which is contracting will not be able to generate the required movement. Now, if they both contract at the same time, my foot might not move, but it may become stiffened. So essentially, what this cartoon is trying to show, that there are two muscles that are required to control single degree of freedom. Actually, I have more muscles than two, but just having two allows me to control the joint torque as well as the joint impedance. And actually we use it so effectively while working out that when I'm moving my arm, a visual representation of my arm movement, people can tell whether you are moving your arm with your joint stiff or loose. I think that kind of representation comes in my motion, right? But this redundancy is there. We need to take care of this redundancy. On top of this redundancy, I also have redundancy of how I'm going to perform the motion. The example I took earlier was that I'm throwing the ball. Now, if I throw the ball fast or slow, you will understand how the ball is approaching, and you can grasp the ball in different trajectories. You need not always move in a straight line. You can actually move in a different line as well. But the way you follow this, you typically tries to have some control on the movements that are being done. This is typically referred to as motor control. I'm putting it in a very trivial way, but there is a lot of interesting aspect that one needs to understand, that why we adapt to a certain situation. So for example, if you're playing a game for the first time, your response might be very stiffened joint response. So I start playing badminton today, and everything I'm hitting is very hard. The more and more I play, I become a little more comfortable. What I mean is, I have learned how this system works. I have learned what kind of muscles to actuate when one particular shuttle is going in one particular direction. So I apply those torques only. So this kind of motor adaptation, motor learning is keep on happening, and I'm learning this new skill. Now, when I'm using a wearable system that I'm going to wear, it is going to add some weight on me. It is going to apply external forces on me. So I'm going to adapt. This is an external dynamics added on to me, just like me playing with a racket during a badminton game, right? So there will be an adaptation that is going to happen. So we as a people who are building these devices need to understand this adaptation to work something out. So with this, I present the last slide on human and robot point of view, that what other information is needed. So I just give a very brief information that from the human side needs to be done. But there are a lot of other parameters that needs to be studied. So I've skipped, I will parallelly run these videos in the background. Typically, when I use this, what I'll ask people to observe is, look at the robot side first. and see what kind of movements are performing, and look at the human side on the right side and what kind of movements are performing, and then let's compare. So with you guys, let me directly do the comparison. Maybe we can watch these videos in the background parallel. So when these two movements are happening parallelly, let me talk about what are the differences that are there in between the two. So if I look at the human system is performing these smooth movements while being very complex. There are large number of degrees of freedom. Robot, when the robot is performing these movements being a less complex system. But what I mean is less number of degrees of freedom, and we can see that in their motion when this is happening. Now, if I talk about the actuators, we use muscles which may be at best work 10 hertz. That is 10 times I can actuate in 1 second. But when I look at these electromechanical actuators we are using, so the one which we are using in the lab, we are trying to run them 1000 times in 1 second. So just look at the contrast. So the actuators are completely different. The feedback loop and the communication that happens within human neurocircuitry and these electromechanical devices, it's a significant difference, right? So the way this communication happens, the control strategy a robot uses is primarily feedback control strategy. The control strategy human uses primarily feed forward. We try to create a model for everything. With practice we improve, right? So there is a subtle significant difference between the way the two system works, and now we want to combine the two system. When we want to combine the two systems to add an advantage, we want to make sure that the neuromechanics part as well as the robot physics part are understood, and such that when we combine them together, there is a movement adaptation, and we understand when there will be a compensation to this. So with this, let's move towards taking some examples from our lab. So what I thought, I will give you a little glimpse of the kind of things that we do in our lab.
Hi, sorry to butt in. So something very interesting. So as I watched the robots, one quick question that came to mind was, so those actions that it performed were obviously not like, I mean, were those fully programmed, or were there simple primitives which were commanded to the robots, which it then deciphered into low-level commands? Just out of curiosity, because when you watch those motions in the left-hand video, they're extremely complex. So what was the the command, the logical sequence for commanding those?
No, I think this video particularly, when I think research about like how these movements were performed, so they were divided into primitives. So they were asked to perform a set of series of trajectory, and then the video was choreographed overall. So it was not a continuous motion, though the scenario has changed now a bit. So there is a little bit more robust low-level control, and some of these movements are being performed in a efficient way. For this particular video, this came around 2019. So at that point of time, there were series of small movements which were choreographed together to make this whole video together.
Yeah, because what's interesting is, when you command simple motion like, walk straight, turn, carry, there's like a very well-defined task.
Yes.
And then underneath that task is the robot maintaining its stability.
Yes.
So the goals are like crisp, right? Whereas if you look at a dance, the question is, what is the task? So stabilization, and how do you define stabilization in that case? So that's what I thought kind of just felt very intriguing, which is how do you define the task, and then what's the notion of stability in those cases?
So actually, this Boston Dynamics, I think they have this video and then explanation of this video as well. I think
okay.
But I think from the robot's perspective, you have directly hit the nail. So we are not yet probably in a state that we can ask a robot to become a dancer, though I think almost 5-6 years have passed since then, and I think the low level have improved significantly. So some robots are being right now. I recently saw a video where they were dancing in sync with human in real time. I think there has been some upgrade in these control strategy.
Okay. And so one final question, I won't labor this any further, but these actions that we saw were not like the outcome of learning by demonstration, right? These were programmed, not something that a robot mimicked.
Yes. This particular video is not supposed to show that understanding. So learning by demonstration, people are doing it, but this is not what it is.
Okay.
This I put it in contrast just to show that when I look at the left side, I do see some motion generated, but this motion is getting generated by a system which is significantly different from a human system.
Of course.
The way human neuromusculoskeleton is, and the way electromechanical and these control strategies are used in robots, they are completely different. If I look at human and robot, we do things completely differently. When I want to combine them, I need to change my approach. So that's the idea I wanted to come to.
Okay, good. Okay, thanks a lot.
Yeah. Wonderful. Okay, so with this, let me show some of the things that we do in the lab before I try to come to the study. Yeah. So from the same human-robot interaction point of view, what we do is we kind of try to go a little deeper into the human side of it, and try to think of human arms and legs more like a kind of a system which has rigid bones, and then there are muscles around it. So more like a musculoskeleton system. And then we like to study its neuromechanics, motor control, and limb impedance, of course, because it's being manipulated, being having so many extra muscles than we need. On the robot side, we try to look at the same aspect, but more from a cable-driven robot point of view, cable-driven serial chain manipulator. So here you will see that these two systems can be put together and combined together, right? On the left side, I have a human. On the right side, I have cables, and but the links that were there, now that has become the human leg. Now, human leg in itself to me, is a cable-driven serial chain manipulator. Then I added cables on top. That's my exosuit. That's the system that will apply external forces, and that I'm also modeling like a cable-driven system. So this is some idea that we are trying to propel, and I will show you some results from these understanding. But the way we are doing is, we like to study the neuromechanics part. We want to study the cable-driven system, and then we want to do the experiment together, and that's what we do. But whenever we have to work with human, we have to start with general observation. We have to observe the kind of motion human do. We may not just simply say that, okay, I'm walking, so I must be following a fixed trajectory. That's not true. When I walk, I manipulate my leg motion, my foot motion. If you try to recreate, it is not going to retrace itself in each gait cycle. All of its parameters will gonna vary, but the motion is periodic in general. So when I walk, I follow a periodic motion. So we spend a lot of time in studying how I'm moving, going upstairs, downstairs. Maybe I would like to use computer vision, or maybe I want to give you a challenging environment that you're walking on a treadmill while playing a game. What it does, it do, it gives add cognitive load onto you, and which basically means that some of the brain resources are being used for both the tasks, which compromise some of your movement. So we want to study how loading you from the cognitive or the motor aspect change your behavior. And then, of course, we want to study professionals. Let's say if I'm a dancer, I'm performing a rasa, and some of you among us might have already guessed what rasa this is. So this is a dancer. She's performing one rasa of Bharatanatyam, and you can know, I think you may watch some Bharatanatyam videos, but you will be able to figure it out what emotion this is getting depicted. Or we may want to study healthy adult behavior, because we are very good at deflecting perturbation. So if you're walking on a treadmill and I push you, how you will be able to avoid these perturbation. So that's another approach that we like to study. So in all these, we are just learning from human what all the capabilities are. How do we perform our movements in general? Then we use this understanding to come to the ideas. Can we use this information to create some algorithms? For example, whenever we use these lower limb exosuit, we need to know what the human is doing. Is the human walking? Is the human standing? Is the human walking over ground? Is the human walking on stairs, uphill, downhill? So what is the minimalistic sensor information that I can use? And for that, we were able to show that if I use just one axis of the gyroscope, a gyroscope being mounted at my shank, I can create an algorithm which can create a classifier, and which can identify my state of motion. Am I walking over ground? Am I walking upstairs? The reason for that is I use my ankle joint to interact with these surroundings, and there is a embedded signature which I am able to capture using that. And again, there is some heuristic that was being built, and now we were able to test it with elderly people as well, and now we are trying to test it with some patient population. We may not get the same results, but we will be able to discriminate between healthy gait versus deviant gait from there. Now, the next thing we do is, so far we have not introduced any exosuit, but we also like to study the effect of this motor task and cognitive task. So for example, we ask a person to walk over ground, and the person is playing a video game in the VR setting. So when the person is walking, there is a ball she's throwing, and she's being asked to score higher and higher. We try the same game on treadmill as well. This becomes a very complex task. In this complex task, probably we will not give this complex task to an elderly person, because they will not be able to process all this information, and they may eventually fall. But an elderly adult can actually do that. So we would like to study how do we collaborate, what kind of strategies we take, and can these strategies then be used to train elderly people. So this is what it shows, that we learn from healthy adults, and then we bring that understanding to the elderly people. From the elderly perspective, these tasks becomes very complex. So for example, you see that the individual is trying to interact with the game that he has been presented to. So it allows us to present a day-to-day kind of complex task in a control setting. So now let's see how do we use wearable system. So we collect data from all this, then we can try to put it in this musculoskeleton system. We create these cable-driven leg or arm modeling, and then we try to create these simulations. So there are these musculoskeleton tools that are available like OpenSim and MyoSuit. We can generate these understanding from the muscles point of view, and we can impart this understanding in these softwares to understand, okay, if I want to create an exosuit, how the response of the person should be. Now, we recently conducted this study. I'm not sure whether I will be able to show the whole video, but the whole idea is you can see that there are 5 different models that are being run. Uh, we collected data from healthy human while performing these data, and musculoskeleton model was trained to predict the fatigue in any muscle. So if it just look at the movement of my arm, it asked me to perform certain actions. So move my arm to point A, then to point B, then to point C. By looking at that motion, it is able to decipher that which of my muscle is fatigued. Again, this is just a small task. Maybe I do not fatigue one muscle. I may have multiple muscle fatiguing, or there could be other muscle related problems that we can use this for. So, but what it does is that in real time, if I'm able to identify which part of my arm needs assistance, I can provide that assistance. But these kind of models can be now developed and trained. So with this, we try to conduct these human robot experiments. So what you see in this video, that there is a person walking on a treadmill, and he's being connected to a cable-driven lower limb exosuit, and this exoskeletons can be arranged in 2-3 different ways. Now, which configuration to use is something that we like to play around and study whether this configuration is better for a task, or this configuration is better for a task. To do that, we also create, I think, this modeling from the cable-driven serial chain manipulator point of view. So we model this system, we've identified their workspace, developed the stiffness profile, and then from the purely robot perspective, and then also bringing it to the human perspective. So, okay, if there is a human neuromusculoskeleton system, then we impart these external cable and apply these forces. How the strategy is going to change, how will I adapt to it? For example, if I ask one of the person to move around a trajectory, and this guy, this exoskeleton is applying external force on it, what it will do, it will apply external joint torques at my knee and hip joint. Now, based on that, there will be an external impedance that will be imposed onto this. Now, when I change this configuration from configuration A to configuration B, this impedance that is added will change. The torque that is added will change, and that I will show. And then the final part is, once we do all this analysis, we are trying to get into these development of this portable system. So I will skip this slide. It's a very detailed slide, which basically brings us to the how this exoskeleton can be combined. So there is a low level, a medium level, and a high level, and a multiple sensor data fusion. But I will just show you this video that if when we develop these kind of system, we must test them with human. And when so this video, what it shows is that the human is walking over ground, and there is a gait classifier that is working in real time. It detects what kind of motion I'm doing, and then it assists me accordingly. When I was walking over ground versus when I'm walking upstairs, the force that is required is different. So my system switch between the two tasks. When the person start walking downstairs, or whenever the person is standing, the system detects and change the force profile, so that there is a collaboration that is going on. So right now what we are doing is we are trying to minimize the size and weight of the system to make it a little bit more compact. So if there are any question at this point, please let me know. And I think I may not have too much time, so I will convey only one study, and if there is still some interest, I can go to the second study. All right, so let me continue. So what I would like to show you, one study that we did from the human-robot collaboration point of view, where we asked this question that, okay, there are various exoskeletons that can be developed. Now, how do we study the effect of different exoskeletons onto the human motion? Because we know that human adapts their walking. So we asked a very simple question that, okay, let's suppose there will be healthy adults that will be walking on treadmill. And what we will do, we'll like to change their gait pattern by applying a force. So if I look at this black line, this is my trajectory. Let's suppose this is my foot trajectory that is going on in one cycle. Now in this foot trajectory, from point A to point B, which is part of this area, is where my exoskeleton will apply external force. And the idea is it will increase my step height. Now we will apply this to a number of subjects, and we will apply this using different kind of exoskeleton. So we chose three different exoskeleton, and I will tell you the reason why we chose this. So these are all cable driven leg exoskeletons, but the way you see, the cables are arranged differently. And not only that, in some cases, some external passive elements have also been added. You can think of this spring as a elastic band that sometimes we wear around our knee. Now, so in one cases, the cables are routed through different links. So this can be considered as a regular arrangement, and this could be considered as a co-shared arrangement. Now, why did we choose these three joints, three configuration? So let me give you a layman understanding how this can be visualized. So let's suppose there are three physical therapists. I went to get my leg treated, and they asked me to walk on a treadmill. Now, the, the therapist will hold my thigh and shank and help me move my leg. They all want to make my leg move along a particular trajectory, but based on their experience and their understanding, they approach three different strategies. The way they use their hands to apply the force, in one case, one of the therapists apply larger impedance on my hip joint and less impedance on my knee joint, and she applies these external forces, and my leg moves along the trajectory. In the second case, the therapist pay special attention, ensuring that she doesn't constrain one of the joint more than the other. Both joints are kind of equally constrained. In the third, there is a large impedance that is built because of the physical therapist help assistance on the knee joint. These pink circles that are being depicted is the byproduct of using these three cable arrangement, and we can show this using maths behind it. So we can consider that each cable has a force F, and then we can actually write from a serial chain manipulator point of view what kind of joint impedance it imposes, and then we can calculate these values, and when we will compute these values, we will find that these configuration impose different impedance onto these joints. But the task remained the same. These all three configurations were asked to apply the torque such that my step height increased during this portion of the gait cycle. So the task still remained the same. The joint torques were applied, but joint impedance was different in each cases. Now, let me come to the results. So this is basically the mathematical modeling part. So I think this basically summarizes everything. So this is purely the mathematical modeling of the exoskeleton point of view. In the first case, as I said, the hip stiffness is more. You can see that when I divide hip by knee, it is very large, close to 10 in part of the gait cycle and almost around 8 in the rest of the gait cycle. In the last one, we wanted hip to be less stiff. So if you see, it is under 1. So the ratio is under 1. In the second case, we wanted it to be equal, but we were not able to find a configuration which made it exactly 1. We were not able to get it, but it is reasonably smaller than the first case. It was above 1.5 and to 2, I think, between that range. So with this, when we conducted the experiment, we average over the group. What we found out are these results. So the task of this experiment was that this blue line is my baseline. So this, when I walk in a typical way, this is my step height. Now, when I was being subjected to the exoskeleton, this red, pink, and yellow are the three trials over time. So this was over 6 minutes. I think these three trials were being recorded, and we noticed that in the first trial, the step height actually increased, and it was supposed to increase because the exoskeleton was applying that upward force. But after some time, it didn't continue. The person actually was not able to increase the step height. When I look at the last configuration, C3, I also observe that the red is higher than blue, but after that, it wasn't so. But when I look at the second one, C2 configuration, the step height increased and it was retained throughout the experiment. Now, when I remove the exoskeleton, what we observed that these subjects actually learned how to increase, or they were continuing to do it. There was a reaction in this. So yellow was not higher, but green is higher. In the other case, the same kind of thing happened. Again, it's not trying to say that C2 is better. The idea from these results I want to convey is, when I change the external dynamics of my exosuit while doing the same task, the human adapts differently. Please note, there were 10 adults who performed C1 configuration, C2 configuration, C3 configuration. So this was a cumulative group result. So what does this result implies? That whatever impedance that was imposed onto the human was undesired, such that I was not able to do my task. In the same case, the knee impedance that was added was undesired. In this case, because they were healthy adults, they prefer the one where both joints were equally loaded. So I will skip these couple of results, I think, which go into finer details, but I will come to the final understanding of this, right? So overall, when we observed these, what we found out that when I use this kind of strategy or this kind of exoskeleton, it implied that the subjects used a distal joint strategy. Now imagine when you are walking and you ask somebody, okay, when you walk, try to raise your foot higher during your swing phase. You can actually do that just purely using your knee joint or your hip joint or a combination of two. And these configurations C1, C2, C3 actually showed all three operations. In C1, the subjects use more of their knee joint. In C3, they used more of their hip joint. In C2, they used both hip and knee together. Now, what it shows, just like those three physical therapists, if they want me to use more of my hip joint, what will they do? They will impart large impedance on my second joint so that I can use my first joint more. So this kind of idea that when we try to brought in, so what it tries to tell from the wearable robotics point of view is that human change their adaptation depending upon the external dynamics. So just building a robot is not enough. We need to understand what kind of physics we are adding onto the human, because human are very responsive about the physics that are getting added. Just to give you a very simple example, which many of us might have observed, just watch a small child when he or she goes to the school. The first thing, when they when they put the backpack on themselves, what they do is they compensate the presence of that backpack. They stoop forward. That's the passive dynamics of the backpack. There is no active dynamics. So if I'm making an exoskeleton for a human and I put on the human and human compensate for its presence, the whole idea is gone. You want to make a device that does not make human to compensate for it. You have to work around that part, right? So the other message is exoskeleton are used for individual with disabled walking, and any unaccounted dynamics can lead to undesired compensatory strategy by the individual. If a stroke patient, I want to use it, they already have a disabled walking pattern, and if I add a device which is supposed to help them, and it may end up creating an undesired collaboration between them. So Aditya, do have some time? I have a one small study. Otherwise, I will skip and then I will come.
Yeah. So if you want 10 minutes.
5-7 minutes only.
Oh, yeah, absolutely. By all means, please go ahead.
Thank you. So along the similar lines, so I just present one more study. So the first one was more from the lower limb point of view. This is more from the back point of view. So many of us ask this question in this field is that, can I build a wearable system that can be used for everybody? Is it a right fit? It is going to help me or not? And these are some important questions that one need to ask. Now, the problem here is, how do I do it? I build a device in the hope that it should work. Then I put it onto the human and I found out, okay, human start compensating for it. So there needs to be some sort of simulation that I can do, some kind of maths that I can do. And that's where these musculoskeleton systems that we are trying to use in our lab. And there are various other ways. But there is another aspect called human in the loop study that we can perform. So for these material handling tasks, there are various tasks we do. So for example, what is being shown is that I'm lifting something and walking around. But in addition to this, there are surgeons who stoop in an awkward posture during the surgery. There are gardeners who cut the grass in an awkward posture while carrying a large amount of weight in their hand. And there are various industrial workers who are performing these tasks. So we know that there are a lot of pain points for these workers. So among them, there is a huge problem related to our back. Actually, common people who are actually not doing any of those tasks, including me, have suffered with this lower back problem while just maybe doing a household chore. So this is an important problem we must take into account, and we see how to find a right solution to this. If I think of the physics of a task like just lifting, there are various aspects. So there is a weight that I'm lifting. There is a force that is going to apply downward. It is getting reflected in my elbow, shoulder, and I can actually do a quasi-static analysis where I can think of the force that it will be adding to my shoulder as well as to my back. Then I can kind of go from the very basic understanding point of view. Okay, there is a force that is coming onto my spine. How do I work it around? I can put up an elastic band between the two, which will basically start including my shoulder and the thigh. And that's the best people have shown. I think just doing this small intervention where they start connecting the shoulder with the thigh, this external elastic member they add start helping us a lot. And then there are a lot of systems that have been built around this with this idea. But the question still remains that how do I know that this device should work for this particular kind of setting? So to do that, we wanted to do this study. So what we did is we created an emulator, and to do that, we created a mathematical model. So what you see that, okay, if I connect my shoulder to my thigh using a series of elastic and inelastic bands, then I sensorized my system. So I put a load cell here, I put a load cell here, so that I know what kind of interaction forces are coming in. And then I enable my system to have variability. So where this P2 point is, I can change the possibilities of those. So essentially, I can create this math around. I will not bore you with all this. This is doable. People have done it, and we can go through these papers. So we develop this math. We study this math's behavior to identify how different configuration can do this task. So for this, we need not do real-time human in the loop experiment. We record human data. We run through the simulation to work it out. But still, whatever we will get may not be the right thing. So what we decide to do is we pick up some good configurations that are possible for a task, and then we create a device like this. So this is our final device, which allow us to change the configuration. So this is thing we call moment arm. So this pulley can be moved forward, backward. This moment arm can be rotated upward, downward, and the elastic band can also be changed. So we have different configurations, and now we wanted to study which configuration will work out better. So in the previous case, I showed a musculoskeleton related study. Here I am showing more in the human in the loop study. So in this case, we recruited multiple groups which used these different configuration, and we asked just the same question: do this task with a set number of times. And then we recorded our muscle activity just to compare which of the configuration could work around. And for that, we measure the critical muscle activation. Let me see. Yeah. So in these figures, what you see, these are the 6 different configuration we chose the device could be used. So it's an exhaustive human in the loop study where human and the robot are being used to conduct this trial. So this is another way of creating these optimization. But what in addition to this, what we wanted to study in this is which configuration helps from the mechanical point of view, and the second more from the ergonomics point of view. Were the subjects comfortable while using these configurations? So we recorded their subjective score. We measured which configuration would be finally gives the less forces. So we converted that into these peak forces. So peak FS, peak FW is the force which is coming onto my shoulder, and the compressive force that is coming in. And we were able to figure out that for a squatting lifting task, C4 is the best configuration that all the people basically end up choosing. And with this subjecting scoring, we also kind of noted that which part of which configuration hurt them more. So let me skip some of these results to come to the final takeaway. So the study demonstrated that the importance of extending moment arm in modulating device to body forces, right? And maybe when I'm doing squatting and lifting, this C4 might work. But if I'm a surgeon, if I'm doing a stooping task, I may need a different kind of setting. So C4 is just limited to this, but the same kind of studies can be done. But overall, what these studies tell us is that careful consideration of the exosuit moment arm can significantly impact the user's comfort while using passive exosuit. And this is an emulator, and this kind of emulator can be designed for a back, for lower limb, and we can conduct these human in the loop study to figure what could be the better wearable device for us while doing this task. So with this, let me stop. I know I went a little bit beyond the time, but let's see if there are still some questions there. Thank you.
Thanks, Vineet. Yeah, you didn't go overtime at all.
Okay.
Like bang at the 50 mark. Lovely. Thank you. There was so for the questions, I think there was a question from Kalyani. Do you still yeah?
This is a great talk.
Yeah.
Thanks, Jit.
Really nice, very different aspect, and a lot of energy in your talk.
Thank you.
I thought I saw 2 hands go up. The first one was Kalyani, and then there was Vraj, I think. Yeah, Vraj, go ahead, please.
Okay, sir. I'm starting. So I am Viraj Gandhi, and I am pursuing my MTech from SIT Pune in robotics and automation. So could you, sir, explain me for robotic arm for that exoskeleton, because I am working on the project of the exoskeleton robotic arm.
So there was let me see. So you're saying explain the robotic arm for the exoskeleton. So
so some case study or some explanation about the exoskeleton robotic arm, because I'm working on the proper robotic arm. So
yeah, so there is a difference between a normal robotic arm, if I say, and an exoskeleton. So a robotic arm, typically the way industrial robotic arm, if you see, the idea there is to create a complete arm, right? So the joints and the motors and all of that are all artificial, right? From the exoskeleton point of view, if I think the human is there, the human is, you can think of, let's purely consider that whatever human is doing, that's a noise to the, or that's a disturbance to the motors that are being attached, because your motors are being asked to move around that. Now, there could be a very simple case that you take a robotic arm, if its anatomy is just like my human arm, and I connect that two, and there will be immediately you will see a problem. The way your robotic arm is developed, their joint degrees of freedom will start conflicting with my degrees of freedom. So just take an example: if you go to gym and do knee extension exercise, so you put the machine on your shank, and if your knee and machine joint is not aligned properly, you will immediately start feeling the pain in your knee joint or the thighs or shank, right? So that's where robotics arms are not typically used as an exoskeleton. Human, on human, these systems are attached. And if they are being modeled as a robotic manipulator, then their degrees of freedom needs to be ensured to be aligned with the human joints. I hope I clarified your question. I'm not very sure that I did.
Yes, sir, but I'm little bit confused, but now I'm searching on that. So thank you, sir.
Good, good. You can write an email. I think I can share some literature there.
Okay, sir.
Okay, thank you. So let's see. There's one more question. Maybe we can take that. Is Preeti Honawar. She also made a remark in the chat window. So she is a physiotherapist working on robotic correction of gaits.
Wow.
Preeti, please go ahead.
Hello, sir. My name is Preeti.
Yeah.
I'm a physiotherapist by background, and I'm sure you must know Charukeshi Healthcare. I work as a R&D physiotherapist with them.
Mm-hmm.
And because I was going through your this thing, and it was very informative for me. First time I'm actually understanding whatever you are talking about. And when you said in the previous question, there was a red flag for me when you said that. I thought I would ask for more clarification. In terms like because I mostly work with lower limb exoskeletons, I do understand how when you took comparison of upper limb exoskeleton to a lower limb exoskeleton, um, is it that, and when you gave an analogy of the gym machine, working on it, so in context of a lower limb exoskeleton, is it because the forces are pretty like more what do you say, um, is very large in amplitude? Is it that because is that making it complex for us to see how the interaction between the human and the exoskeleton is working? I don't know.
So
Maybe my
your
question may be a
question is
little vague.
more on the upper arm exoskeletons and lower arm lower limb
No,
exoskeletons,
no,
right?
mine is more. I work with only lower limb exoskeletons
Yeah, yeah.
because in like as a physiotherapist point of view, I feel that upper limb exoskeletons are not that effective rather than end effector
Okay.
organs.
Got you, got you,
So
got you.
yeah,
So yeah,
because
so
yeah.
wonderful. So actually, in our lab, we are also we develop more like a soft exosuit right now, wearable perspective. So we have developed a leg, and we are trying to see if we can use it with stroke patients. So parallelly, we are also working on creating elbow and shoulder and hand exosuit as well. I understand your question. So my take on it is, see, when you see lower limb training, typically they are very task oriented, and most of our lower limb tasks are very defined in a periodic manner. So if I'm walking, I'm bound to take a periodic trajectory.
Yes.
There is a repetition of sort. There are some events that keep on happening. Similarly, if I'm just asking them to do a sit to stand task, there is a set of series of tasks that I can perform. But when with upper limb, it becomes even more complex, right?
Yeah,
So the
environment factor becomes a very big.
Exactly. So because it's a free manipulendum which is moving around, so the task does not get constrained specifically. Though there has been some studies which are showing some improvement in stroke patient while performing day-to-day activities. So now onwards, what is going on that they ask these subjects to wear these exosuits and make them perform some task, for example, this pick and place task, and I think there is this I'm forgetting the name, but I think they put something in a
Yeah.
box, something like that. So those tasks are also being conducted.
Yeah. That's really nice. I get the perspective now because more in terms of biology, how we think about it is lower limbs have more CPG activities like central pattern generators,
Yes,
and rather
yes. Yes.
the more coordination is required for upper limb.
Yeah.
But the forces that we use are very significant in like lower limb, like because the muscles are bigger and the force applying to it also is bigger.
Yeah.
In our practice as well, we have seen that whenever there were certain joint spaces that were breaking down, more frequently because even spasticity is larger and the force production of after spasticity also is like quite significant, and that has been a good learning for me. And this has helped, your talk has also helped me understand a little bit more. Thank you so much.
Thank you. Thank you.
Vineet, so there are two questions in the chat window.
Okay.
So they're from Kalyani. So she's a research scholar in data science at IIT Guwahati.
Okay.
So the first question, so I'll read out both questions if you wish. So the first question is, was any sensor-based feedback used for easy movements? And I believe this was probably a reference to the first study.
Mm-hmm.
And the second question, she said it pertains to the second study. And what she asks, sort of quote, is, are those results task specific, or have they been tested on regular movements of body, such as walking, sitting, for posture enhancement? Since bad posture causes pains, which most of us feel.
Yeah. So let me answer the second question first. So yeah, the whole study was very task specific. So the whole motivation of that study was, let's suppose if I identify a task which is causing problem in my lower back, what sort of device I should build, right? So for that purpose, we chose squatting, lifting, lowering task, right? But if I was to do a different task, for example, I lift a weight and walk, the same configuration might not be the right configuration. So you're perfectly right that those results are subject specific. If I start doing something else, my device configuration approach needs to be changed. So that was clear. From the first point of view, yes, I think when we use any exosuit, we have to use wearable sensors to make sure that our device is working correctly. Maybe as a product, I might want to try to reduce the cost, and I might get out of those. But in our lab, we sensorize every bit of it, so that I think we can control, we can present our results, so we can get published as well. So as of now, all of our devices in the lab are redundantly sensorized. uh, so we do collect that data, and most of this data is used in real time as a feedback control, and afterwards as a post processing to analyze the performance, whether our device was useful or not useful. Thanks for these questions, Kalyani.
Right. And I think, I think along those lines, Vinit, I mean, there's no reason why we should shy away from sensors. I mean, if you think about just the human limbs, I mean, we have sensors at pretty much every joint and throughout, I mean, even the skin, I'm pretty sure, would
Yes.
feedback into the gait, although the skin is not technically part of the motion itself.
Yeah.
So, I mean, there's no reason for us to shy away from sensing in that sense,
It's just to reduce cost from the product point of view.
That's true. Yeah.
And wear and tear.
Yeah.
Wonderful.
Okay. Yeah. All right. Great. Any other questions? So if there are no questions, Sujit, go ahead. Sorry.
No, just to say thank you. Thanks for
Yeah,
Vineet.
yeah. Thanks, Vinit. That was a really wonderful talk. Yeah.
Thanks, Sujit.
And we
Thanks.
also got time for quite a few questions as well. So this was great. So thank you very much, Vinit, again. Well, obviously we can't applaud over over Meet as we usually do. But yeah, I think there's an implicit applause from I think from all of us. This was a great talk.
Yeah.
Thank you. Much appreciated. Thank you.
Yeah, thanks. See you again next Thursday.
Yeah.
All right.